Okay, so today we'll discuss the frequency response of the common base amplifier, both the low frequency and the high frequency. And then we'll look at the approximation methods that we have discussed in the last couple of lectures, add some comments to it. So this is the common base amplifier we had studied in lecture 7. Okay, so I think lecture 7 may have been the DC circuit, the common base we added later. So the DC circuit we have studied and used at great length. So this is just a recap of all the voltages and currents in the circuit, and these are the AC quantities R pi GM. And then, like the common emitter amplifier that we discussed in the last two lectures, let us assume that CE and CB are 2 millifarads, these two the capacitors. C pi is 4 pico, C mu is 1 pico, and RS is 1 kilo ohm. So you recall from the discussion on the common base amplifier that this CB is connected to reduce the resistance looking into this node, and the overall gain increases. I forget which lecture number this was, anyway look it up. Okay, so this is a circuit we'll analyze for low frequency and high frequency now. So let's we'll start with the high frequency analysis. Okay, so that is basically from lecture 13 slide 7, but now we've added the two high frequency capacitances. So let's quickly do this. So for high frequency, CE will be short circuited, so RS will get connected to the emitter node, and CB will be short circuited so that the base node of the transistor will be at ground, and of course this is at ground in the small signal circuit, so R1 and R2 both will be grounded or shorted to themselves, and so will not appear in the small signal high frequency circuit. So that's what this circuit is, R pi, RE, RS and RC. Okay, so now we have two nodes and we write two nodal equations. So the nodal equation at the VO node is VO by RC plus SC mu VO minus GM VE equal to 0. So incidentally, this is GM VBE flowing down, but this is our base node, it is at ground, so VB is 0. So this is pointing upwards, GM VE. If we solve this, we get VO equal to GM RC by 1 plus SC mu RC into VE. And then we write another nodal at the emitter node. So we'll get VE by RE, VE by R pi, SC pi VE plus VE minus VS by RS plus GM VE equal to 0. And then there's only VE and VS here. So we combine all the VE terms and that becomes equal to VS by RS. For now, let us call this quantity, the three resistors. They are obviously, these are like three resistors in parallel here. So let us call that parallel combination as 1 by Rx. So we'll get VE into 1 by Rx plus GM plus SC pi equal to VS by RS. So that is written here. And so we find an expression for VE in terms of VS. So this whole thing goes on the other side, Rx by RS, all this. So we have VE in terms of VS. Here we have VO in terms of VE. So here we substitute for VE from this expression and combine, and we get this expression for the transfer function of the common base amplifier at high frequencies. So this is one form, but we still have this Rx, which is kind of we need to put that back. So let us do some manipulation of this. So Rx GM RC, we take this 1 plus GM Rx out. So you'll get 1 plus SC mu RC and 1 plus SC pi Rx by 1 plus GM Rx, because that 1 plus GM Rx went out. So now this is the form where this is the low frequency gain and the circuit has two poles. So let's make one comment here. So in this circuit, there is no capacitance between the emitter, the two nodes for which we wrote our nodal equations. And when this happens, this has other consequences, but for now, when this happens, then the transfer function has this form of two first order terms in the denominator rather than having a second order quadratic equation. For the common emitter, we had a quadratic because there was a capacitance between the two nodes for which we wrote the nodal equations. Okay, so that's one observation. Now let's simplify this further. I'm not sure simplify, but write it in a different form. So this is the low frequency or the mid-band gain. And then I'm doing some manipulation. So I've taken the Rx out. What have I done? Yeah, I've taken Rx out and that Rx cancels with this. So you get GM by Rs into 1 by Rx plus GM. And then 1 by Rx, I substitute back the quantity which it was defined for, so that we get this back. And then I'm saying 1 by Re plus 1 by apply plus G. There's a reason I'm doing all this. 1 by Re plus 1 by apply plus GM, these 3 out of these 4 terms, is equal to 1 by Re plus 1 by apply plus beta by Rpi, because GM is beta by Rpi. And then these two last terms can be combined. So you get 1 by Re plus 1 plus beta by Rpi. Now this quantity, if you recall the common base amplifier, is the resistance, input resistance of the common base amplifier. So let's go back at this circuit. That quantity R pi in parallel with 1 plus beta into, Re parallel 1 plus beta Re. Now Re parallel R pi divided by 1 plus beta is the resistance looking into the emitter node of a common base amplifier. We've done this before, so I'm just recollecting that is the resistance. So that is what we've got here. Re parallel R pi divided by 1 plus beta. That is the input resistance of the common emitter amplifier. So all these things, so these 3 terms here, can be substituted by 1 by Rin. So we get 1 by Rin here. GMRC, all this, so GMRC out, and all this we can write, so you multiply and then RS cancels and we get Rin by Rin plus RS. So this is a nice form, and we've seen this form for the common emitter amplifier also. What this is telling us is that the mid-band gain or the low frequency, mid-frequency gain of the common base amplifier intrinsically is GMRC, but because of the source resistance there is loading, and so that loading is represented by Rin divided by Rin plus RS of the input voltage Vs. So this is the overall gain of the common base amplifier. So this is intuitively a nice way of writing the mid-band gain, where Rin is this big quantity. Okay. So this is the low frequency gain, and this is the overall transfer function, low frequency gain and the 2 poles. Now let's look at the numbers. So the Rin, which is 1 by Re plus 1 plus beta by Rpi, is all this, which is very small. You recall that the input resistance of a common base amplifier is small. Because of this Rpi by beta factors, Rpi by beta is just about 25 ohms. So the overall input resistance is also just about 25 ohms. And the mid-band gain, which is GMRC times this loading factor. So GMRC is large, nice 240. But because Rin is very small, there is an immense amount of loading. And so this term is very small. And so the overall mid-band gain turns out to be only 6 because RS is large. So note that if RS was smaller, of the order of the Rin, then this gain could, for example, be one could say 120 if RS is equal to Rin. As you recall, this could be the case for maximum power transfer. But in any case, for our circuit, the gain is 6. And the 2 poles, The first pole is 1 by C mu RC, and we put the numbers and it comes out to be 26 megahertz. So I have divided this by 2 pi to write this in megahertz, and the second pole is GM by C pi, which is 1.6 gigahertz. Okay, so let's do a quick comparison between this and the common emitter amplifier. So we have the common emitter expressions, common emitter numbers, and common base expressions and common base numbers. So the input resistance is moderate, very small, mid-band gain good, very small. The 3 dB frequency of the common emitter amplifier was small. Here it is much larger. The second pole is in fact the same, approximately both of them are GM by C pi, so they are the same. Now this is an important distinction between the common emitter and the common base. As I just said, the gain of the common base could be as large as about 120 for our circuit if the input resistance is RS is the same as the input resistance. This difference will still remain independent in fact of RS of the common base, because the common base doesn't even depend on RS. What we notice is that the 3 dB frequency of the common base amplifier is much larger. And if you compare these two expressions, we see that this C mu RC is common. The common emitter has this additional GM RS parallel R pi. And this basically, if you recall, comes from C mu being a Miller capacitor. C mu was connected between the input and the output of the common emitter amplifier, and therefore it experienced the Miller effect. And so its effective value on the input side was multiplied by GMRC, and so this became the effective capacitance. The common base amplifier does not experience Miller effect. So let's go back to the circuit. So okay, so I mentioned this just a little while ago. There is no capacitance between the input and output of the common base amplifier because of the construction of the bipolar transistor, and because there is no Miller capacitor, there is no Miller effect experienced by the common base amplifier, and therefore the poles of the common base amplifier are at a much higher frequencies, the dominant pole, compared to the common emitter amplifier. So this is a very big advantage of the common base amplifier. It is much faster, or it can achieve much larger 3 dB frequencies. In fact, not in this specific example, but suppose you were to consider the case of RS equal to say 25 ohms. If RS was 25 ohms, everything else will more or less remain the same here, and the gain will become 120. So consider a gain of 120, then the gain bandwidth product of the common base amplifier will be 120 times 26, which is far greater than the gain bandwidth product of the common emitter amplifier. So inherently, common base amplifiers achieve much higher frequencies. Alright, this is an important distinction. Alright, let us look at the low frequency analysis of the same circuit. We look at the effect of CB and CE. So these are, I've just repeated these for reference. One thing I have done is I have removed the source resistance from this circuit. It turns out that when we solve this circuit, if RS is included, the equations become just too complicated and they are very difficult to handle on paper. I should not say very difficult, very tedious, and I did not want you to go through that tediousness. This is a manageable circuit, and I expect that you will solve this circuit on your own also. The solution is here. We'll go through it, but you must solve it on your own also. So I should make a general comment here. This is valid for whether this is a recorded lecture or a physical lecture in the classroom. Uh, teaching, learning anything, and specifically electronics, is similar to learning swimming. I may have said this, but I'll say it again. Imagine that you have a set of video lectures or recorded lectures on how to swim, and the instructor explains the different styles of swimming and what you do first and what you do next, and the instructor himself goes into the water and demonstrates how to swim. You will not learn swimming by watching video lectures of swimming. You have to do it yourself. You have to go jump into a pool and into the water and swim yourself. Then only you learn swimming. Same is true here. Unless you solve these circuits yourselves, you are not learning all this that we are going through. This what I am going through is just to help you do it yourself. Okay, having said that, let us do this analysis. So this is a small signal circuit for low frequencies. So CE and CB are there. Everything else is as it is. So again, two nodes, actually three nodes, I'm sorry. But this is trivial. VO is trivial. So VO is minus GMRC VBE. Let us define, I have defined RB to be R1 parallel R2, the two biasing resistors. Okay, so we write the nodal equation at the base node, VB by RB, SCB VB, VB minus VE by R pi equal to 0. And this has only VB and VE, so we can solve for VB in terms of VE. There is only one VE term. And we'll get VB equal to RB by R pi plus RB plus SCB R pi RB VE. At the emitter node, we have four terms, 1, 2, 3, 4. So V minus VB by R pi plus V by RE plus SCE VE minus VS plus GM VEB, which make this VEB, it becomes plus. So we have four terms. So we solve this for, we'll write an equation for VE, VB, and VS will go to the right hand side. So I've written that again, and if we multiply out by RE R pi and combine terms, we'll get this. And now if we substitute for VB from here in terms of VE, so on the left hand side, this VB will get replaced by something in terms of VE, and we'll get this one big expression. And then if we, so this denominator gets multiplied by this minus that, and the denominator also goes to the other side, and so we'll get VE into some very big thing with an S squared term, and on the right hand side we'll get SCE RE R pi VS and this denominator. Okay, and then we solve VE in terms of VS. Okay, so this is so notice that here there is an S term, constant plus S divided by constant plus S times something plus S squared times something. Then I am taking in the numerator the CB R pi RB out, and so the S will remain. It's S plus R pi plus RB divided by CB R pi RB, that is this. And then what comes out is CB R pi RB, that goes out, multiplied by CE RE, and then I am taking that to the denominator. Alright, so that goes away, so we get S into S plus R pi plus RB divided by CB RB R pi, and this thing which was at the top has gone, divides each of the denominator terms, and it turns out that the coefficient of S squared was the same. So that goes away. So we have S squared with a unity coefficient and these two big expressions. Okay. What we want to find, of course, is VO. So let me go back. So we got VE in terms of VS. We want to find VO, which is minus GMRC VBE. We found VE We know VB in terms of VE. So we need to put all of this together. So let's put it all together. So VB is this. So VEB is VE minus VB, which is equal to VE into 1 minus VB by VE, and VB by VE is this. So so this is 1 minus this. So this goes up and RB cancels. So we get VEB equal to VE into this. All right. And then we take out a CB R pi RB from here. So the S remains and the CB R pi RB comes out. And so this will be S plus R pi by CB R pi RB. So that R pi cancels and we get this. In the denominator also same is there, CB R pi RB. So we take it out and we get this. So VEB is equal to VE into a ratio of 2 terms. Now, so this is VEB and VO is GMRC into V. Okay, let's go back. What is V? VO is minus GMRC into VBE. So if I make this VEB, the negative will go away. So we get VO equal to GMRC into VEB. So VO is equal to GMRC into VEB, which is this. Which is this. All right. Which is this into VE. And VE we found already. So all this. Okay, so you go through this. I think it is too much to try to explain this in detail. As I said, you have to do it yourself. So this is the expression we get. Eventually, this is the transfer function VO by Vs, low frequency transfer function for the common base amplifier. Okay. So this is a transfer function. Now let us see if we can get this the same, that minus 3 dB, the lower cutoff frequency from the time constant method that we had discussed, I think the last lecture or the lecture before that, last lecture. So we saw that the lower cutoff frequency can be written as the sum of individual frequencies caused by individual capacitors. So we say omega L is 1 by Rx CB plus 1 by Ry CE, where Rx is the Thevenin's resistance seen by CB, which CE short circuited, and Ry is the Thevenin's resistance seen by CE, which CB short circuited. So this we had defined last time. So let us find Rx, Ry. So this is the circuit. So if we draw this with CB short circuited, we'll get the Ry, and we short circuit CE, we'll get Rx, and of course Vs is short circuited always for finding the Thevenin's resistance. Okay, so if we do this, so if CE is short circuited here, then what is the resistance seen by CB, which is Rx? So if we look at this, it is RB, and this node is shorted to ground, so RE is shorted to ground. This is gone, so only R pi is left in parallel with RB. So we get Rx equal to RB parallel R pi. For finding the resistance seen by CE, which is basically the resistance looking into the emitter and ground across these two nodes, this is short circuited, so RB goes away, R pi comes in parallel with Re. Or actually, okay, one can look at it either way. In fact, this is simply the input resistance of the common base amplifier, which can be written as Re parallel R pi parallel 1 by Gm, or this is beta by R pi, whichever way one wants to write it. So there we found Rx and Ry. So let's write the expression for, so Rx is this. Okay, so what was this? Rx was this. So I'm writing this out, Rb R pi by R pi plus Rb, and Ry is this. So I'm expanding this, and Gm is beta by R pi. So we get 1 by Ry equal to 1 by Re, 1 by R pi plus beta by R pi, and we combine this 1 plus beta Re, and then if we combine these two, we'll get R pi plus 1 plus beta Re divided by Re R pi, and so we get omega L equal to this big expression. Now if we compare this, so this is I've written omega L here, and this is a transfer function we derived. So the coefficient of the first order term is the same as this. So identical they are. So this kind of once again verifies that this quantity which we found without solving any nodal equations does actually correctly give the lower 3 dB frequency of the circuit. All right. Now there is a very subtle point, interestingly so, after all these years I myself had not noticed it until yesterday. So I thought I should kind of point this out over a couple of slides. So you recall that we had in lecture 18, we had described an approximate method for finding the roots of polynomials, and we had taken an example of a quadratic. So I want to go through this again and make a point at the end. So let's say we are given a quadratic as squared plus bs plus c equal to 0. Now to make our approximation, it is required that we make either the coefficient of the s squared term 1 or the coefficient of the constant term 1. We'll see that very quickly. So let us do this. So let us make the constant term 1. So what we do is we'll divide the equation by c. So we'll get a by cs squared plus b by cs plus 1 equals 0. The right hand side remains 0. And now we say let the roots of this polynomial be p1 and p2 with the same assumption that p1 is much less than p2, so that we can make the approximation. Now, given this form, because this constant term is 1, we can write the factorization in terms of the two roots as 1 plus s by p1 and 1 plus s by p2, because in this form even the right hand side will have a constant term which is equal to 1. Okay, so we did this earlier, lecture 18. So we expand this out as 1 plus s into 1 by p1 plus 1 by p2, and then we say p1 is much less than p2, therefore 1 by p1 is much greater than p2, so we ignore the p2 and we write this as 1 plus s by p1 and s squared by p1 p2. Alright, so this we did before, and then we say okay, p1 is this and p2 is this. Okay, this is what we did before. Now let's look at the same polynomial again. as squared plus bs plus c equal to 0. Now let us make the s squared coefficient 1. So let's divide this equation by a. So we'll get s squared plus b by as plus c by a equal to 0. Now of course, I'm sure you know that this equation and this equation and this equation all have the same roots. The roots of a polynomial do not change if we multiply the polynomial by a constant. It's kind of obvious. So I will not prove it, but it's understood. So we know that the roots of this are also p1 and p2, with p1 much less than p2. Now we say, but because of the form of this, when we factorize this, we'll write it in this form. S plus p1, s plus p2, because the coefficient of the s squared term is 1. So we have to write it in this form, only then will this match with this. So we say this, and then this is s squared plus s into p1 plus p2 plus p1 p2. Then we say, well, p1 is much less than p2. So in this s term, p2 will dominate. So we'll get sp2 plus p1 p2. And then we can make the approximation again that this is equal to this, and then okay. So I've written the first form and the second form. The first form was a by c s squared. The constant term was 1, and here the s squared term has a coefficient 1. So I've written this here and I've written this here. Well, p1 and p2 are the same, and p1 is much less than p2 is the assumption in writing these two equations. So what we notice here is that the coefficient of the s term in this form of the equation is 1 by p1. in this form of the equation, the coefficient of the S term is P2. Now suppose we had an nth order polynomial rather than a second order polynomial. You can show this, it is kind of easy to show, and we'll assume that all the n roots of the polynomial, the n poles, are spread far apart. So we make this assumption P1 is much less than P2 is less than much less than P3, and so on up to Pn. So P1 is the smallest frequency or the root, and Pn is the largest frequency. All right. So the root of, in this form, the coefficient of S is 1 by P1, whereas P1 is the smallest frequency. In this form, the coefficient of S is P2, where P2 is the largest frequency. All right. In this case, we have only 2, so there is one smaller and larger. But if there are n, you can easily show that this will be the largest frequency. And this is an important point to recognize. Okay, so this is a plot from lecture 18, the complete frequency response of our common emitter amplifier. The point I want to make is, if I want to find the upper cutoff frequency of an amplifier, that is this, the upper cutoff frequency. So in the high frequency analysis, this is the lowest of all frequencies. So I'm trying to find P1. If I have P1, P2, P3, P4, I'm trying to find P1. If I want to find the lowest, the lower 3 dB frequency, it is this I'm looking for. So in the low frequency equivalent circuit or the transfer function, and of course there are many frequencies on the lower side, this is the highest of all frequencies. So this is the Pn if there are n terms, or it's an nth order polynomial in the low frequency transfer function. All right, so this is an important thing to recognize. And then we say that the time constant method allows us or defines P1 to be found by the open circuit time constant method, and Pn by the short circuit time constant method. All right, so if I have many poles on this side, the open circuit time constant method applied to the high frequency transfer function or the high frequency equivalent circuit gives me P1. If I were to find the short circuit time constant, or I should find, if I were to apply a short circuit method to find the frequency, that will give me P2. Where is P2? Here. This one is P2. All right. And if there are n, then it will give me Pn, the highest frequency, the short circuit time constant method. Similarly, for low frequency, the short circuit time constant method will give me this Pn. The open circuit time constant method will give me this if it is the lowest or whichever is the lowest frequency. So both can be applied on both sides, but of relevance is short circuit for the lower and open circuit for the upper. Alright, so now let's go back to our low frequency response. So we just derived, I'm writing these equations again to show that this denominator is written in the form s squared plus as plus b. The s squared term has a unity coefficient. Therefore, this corresponds to P2, the upper or the higher of the two frequencies, because this is the low frequency response and I have to find the higher of the two frequencies, and that is equal to this. Okay. That is that. Next lecture we'll do emitter follower high frequency analysis.